So we're going to complicate things a little bit by having a charged, infinitely large conducting sheet next to a charged, infinitely large insulating sheet. So first, let's take a look at what charges they have when they are completely isolated from one another, when they're all by themselves out in space, not influenced by anything else. The insulating sheet has a sigma of +3 coulombs per meter squared. And the conducting sheet, when it's all by itself with no other charges or fields around it, it has a left and a right surface charge density that are equal, and they're both -2 coulombs per meter squared. So now we're going to bring these two objects close to each other, and they're going to interact with each other. The insulating sheet, nothing happens to that. Those charges have to stay where they are. But on the conducting sheet, they could rearrange themselves. Okay, so here I've drawn the insulator in blue. I'm calling that sigma sub 3. And the conductor, the charge is going to split up somehow. And I'm not sure how it's going to split up. So I'm going to call the left side sigma 1 and the right side sigma 2. And once I put down sigma 1 and sigma 2, the final charge densities of those two surfaces, then I can treat them as two insulating sheets of charge, and I can go ahead and find the electric field everywhere, with the condition that in between those two sheets, E has to be 0. So I have two equations, and I have two unknowns in this problem, right? Sigma 1 and sigma 2. So my first equation is that sigma 1 plus sigma 2 has to add up to be -4, right? I've got a -2 on either side of my original surface. And my second condition is that the electric field is 0 inside the conductor. So let me go ahead and fill in the electric fields. From the insulating sheet, I'm going to call those E3 since I used a 3 over there. Everywhere to the right of that sheet, the electric field is going to be pointing in that direction. Oops, that's a 3. And everywhere to the left, it's going to be pointing to the left. And I'll switch colors for the other sheet. I'm just going to draw my lines in as if these were positive charges. I'm not sure if they're going to be positive or negative yet, but I can take that into account. And then in red, we'll draw the electric field from the right side of the conducting sheet. And I'm going to call my positive direction to the right. So I've got a condition here that the net electric field inside my conductor, that's E3 plus E1 plus E2, those are all vectors, has to be 0. And I know my electric field from a insulating infinite sheet is sigma over 2 epsilon naught. So I end up with sigma 3 over 2 epsilon naught. That's in the plus x hat direction. Plus sigma 1 over 2 epsilon naught. That's also in the plus x hat direction if sigma 1 is positive. And if sigma 1 is negative, it gives me a negative sign here, puts it in the other direction. And the last one is going in the, if sigma 2 is positive, it's going in the negative x hat direction. So I'll put it like this. And if sigma 2 is negative, it flips that and puts it in the positive direction. So I'm going to simplify this a little bit. I get sigma 3 plus sigma 1 minus sigma 2 is equal to 0. And I have two unknowns in this equation, so I need another equation, and the other equation is the equation 1 up here. Sigma 1 plus sigma 2 is equal to negative 4. So that means that sigma 1 is minus 4 minus sigma 2. I can substitute that back in. I also know what sigma 3 is. That was given in the problem. So I substitute those two things into that equation, and I get 3 minus 4 minus sigma 2 minus sigma 2 is 0. And I get sigma 2 is negative 1/2. And that means that sigma 1 is negative 3.5. Because when I add them together, I have to get negative 4. So I've got, let me just redraw. I'm going to pause and redraw my setup. Okay, so this is the same graphic I had earlier. The only difference now is I have changed the directions of the E fields for sigma 1 and sigma 2, or what I'm calling E1 and E2, because I know now that sigma 1 and sigma 2 are both negative. So I have indicated the proper directions of the E fields. So now I can find the electric field everywhere. So let's start right here. I'm going to call that region 1. So in region 1, my electric field is going to be the vector sum of E3, E1, and E2. And E3 is sigma 3 over 2 epsilon naught in the minus x hat direction. I guess I should put magnitudes on here because I've taken the direction into account in the vector notation. And I've got my E1, which is sigma 1 over 2 epsilon naught, and it's going to be in the plus x hat direction. And I've got a sigma 2 over 2 epsilon naught in the plus x hat direction, and I need to add those up. So I've got 3 minus 3 over 2 epsilon naught plus 3.5 over 2 epsilon naught plus 0.5 over 2 epsilon naught, all in the x direction. And I get 4 minus 3 is 1 over 2 epsilon naught to the right. So that's the electric field in region 1. Do the same thing for region 2. I'm just going to add them up. And they all point in the plus x direction. So I've got 3 over 2 epsilon naught plus 3.5 over 2 epsilon naught plus 0.5 over 2 epsilon naught, all in the plus x direction. 7 over 2 epsilon naught. Now, let's verify. I'll call this region 3. Let's verify that E is 0 inside of our conductor. So E3 is in the positive direction, and E2 is also in the positive direction. And what do we have? We've got 3.5 minus 3.5. We got 0. Excellent. Check. It worked. And let's go back and do the last region. Call that region 4. And the only one that's in the positive direction is E3. And I've got 3 minus 4 is minus 1 over 2 epsilon naught. So what we ended up with was that the charges split. Sigma 1 became negative 3 halves, 3 and 1/2, and sigma 2 is negative 1/2. And let's think about that for a second. What happened was, with that conductor, let me draw it down here. Here's our insulator, plus 3. Here's our conductor, with a total of minus 4 on it. Well, if there's plus 3 on this insulating sheet, then we have to have, over here, we have to have minus 3 to cancel out the effects of the plus 3. What does that leave? That leaves negative 1. The negative 1 has to split equally between the two sides, or we're going to be left with electric field in the middle. So the negative 1 then splits, and we have negative 1/2 on each side. So the plus 3 on the left, that insulating sheet, told us we had to have negative 3 on the left surface of our conductor. What was left over? Negative 1. That had to split equally. And so on the left side, we've got negative 3.5. And on the right side, we have negative 1/2.